Our tipping point topic is the Atlantic Meridional Overturning Circulation. So, the Atlantic Meridional Overturning Circulation, or the AMOC, is the Atlantic Ocean's conveyor belt. It's a system of ocean currents that circulate water throughout the Atlantic Ocean. Warm, salty water flows north and then it cools, becoming dense enough to sink, which drives the current. And it influences climate and weather patterns through its transport of heat and ventilation of deep waters.
A tipping point can be described as a severe change of state in a system that is irreversible and often consequential. A tipping point that can be described for the AMOC is a threshold where freshwater input, warming, and density laws become so strong that deep water formation collapses, pushing the Atlantic circulation into a weaker off state. This is done by freshwater and warming, weakening the density of the water, salt advection feedback, amplifying the slowing of the water, which basically means that basically the rate that this water flow is moving from around each region across the world. Basically, it slows down until it basically just stops. Circulation rapidly reorganizing. This is basically like the shifting of the water, causing it to expand, reducing the density once again. And it's hard to restart for centuries. Once these processes start to slow down, what happens is it takes centuries for it to basically re-amplify itself to start back up and keep moving. One of the tipping points is salinity levels. Lower salinity means less dense water, which means there's no sinking. If the water doesn't sink, that means that there's circulation is basically isn't circulating. When the North Atlantic becomes too fresh, the surface water can no longer sink. The fresh water enters and lowers the salinity, and then once that happens, there's less sinking. And once there's less sinking, the AMC starts to slow down. And basically, the water kind of just stays there. There's no basically overturning of the water. The slower AMC now brings in less salt water, which then once again makes it even more fresher and creates a feedback loop. Once this feedback loop is started, it's kind of hard to stop it because it's basically amplifying its own destruction. And as you can see over here on this graph right here, as the AMOC strength, it was very high 70,000 years ago. But as you can see, right around 30 to 20,000 years ago, it kind of it bottoms out. Once again, and then it started to rise, but then as again, it's starting to sink again. They did studies where they amplified these tipping points to see what would happen, kind of simulate what would happen if the AMC were to completely lose strength. Would it come back? Would it kind of go low? Would it kind of fight back? And these are basically just some graphs explaining how the water works. As you can see over here, you have the warmer climate or the warmer temperature of the water, and you can see the depth of the water as it goes. And then when it's not such a warmer climate, you see how it kind of circulates. It forces the warm water is basically forcing the cold water back down to the bottom. It's not circulating. It's not layering correctly. Here you can see that the CO2 rates are affecting the overturning strength of the up pathways. They're up of the AMOC. So high CO2 rates weaken the AMOC. Warm air melts the ice faster, once again putting fresh water into the ocean, making it less salty. Warmer oceans expand, so I was talking about before, the ocean basically as thing heats up, it expands, that's as you can see in most things. This causes the water to expand and stratify, which basically means it causes the water to expand and kind of layer itself. Which you can see back on the previous slide, how when they start to warmer, you see that there are two layers of water, but on the not so warm water, there's only that one layer, that one circulation of water. Surface waters warm and become less dense regardless of salinity. So yeah, even if the salinity didn't change, if the water is too warm or past a certain threshold, it just doesn't matter. The warm water will kind of just stay there. It wouldn't sink. If the warming continues, the AMC will be pushed into a no return zone. Basically, this means that it's that threshold, that point where it's like, okay, we can kind of bring the AMC back, and then below this threshold is like the AMC is gone. It's going to keep slowing down until it eventually stops. But they ran multiple tests, and they subjected the AMC to 4 times the CO2 rate. And what that basically showed was that, like, even though the AMOC was under pressure on a lot of the CO2, it didn't fully disappear. It kind of slowed down to like the most slowest it could go, but it still was there. It didn't disappear. So they kind of use that evidence as a saying that, oh, okay, the AMC is weakening, but it might not actually disappear. And it's also, you can kind of relate that back to it, taking a few centuries to it reestablish itself, which kind of makes you think that, it never actually goes out. It just goes to such a minimalistic scale of movement that it's kind of hard to track. It's almost as if it's not there. But here on this graph, you can see that the total carbon dioxide in the atmosphere has an effect on the overturning strength. As as the total carbon dioxide increased, the overturning strength decreased. And you can see here that, when they then decrease the concentration of the concentration in the atmosphere of carbon dioxide decreased, and you can see that it kind of started to rise back up. But even though it was decreasing, though, it stayed the same. It didn't go back up. It's too low. It crossed that threshold once again. It was kind of too low for it to pick itself back up. So now it's gonna keep slowing down until it reaches that point to where it can no longer do it.
A lot of the trees in Europe, so there'll be drier, cooler conditions that are expected, and they'll decrease the tree diversity. And past models show that this has happened once before during an ice age, which made Neanderthals no longer able to inhabit the area, so they moved out for a handful of years and then finally moved back in when it was a stable climate. The hagfish is kind of following that escalator to extinction in the ocean, so they are moving more poleward, and they are a big source of food for humans. So if they become less available, it will impact our resources. And humans are expected to be impacted, especially in South Asia and Asia. They rely very heavily on monsoons for their food and growing seasons and access to water, and the weaker and less frequent monsoons will leave parts of the world scrambling for resources. Effect on ecosystem functions. So the tropical moist forests will be affected, so that's like the Amazon rainforest. The models show declining vegetation, with the AMOC slowing and weakening, less rainfall and moisture is available in the Amazon, causing drier conditions, which is expected to allow for more savanna-type vegetation to take a hold and expand in the area. So this is your grasses instead of leafy plants. There's roughly 30,000 endemic plant species in the Amazon, which means we will lose a ton of genetic diversity. And losing the rainforest will also drive CO2 emissions even higher than they already are, as there's about 30 tons of CO2 trapped in the forest. So ocean salinity and ocean temp go hand in hand. The salt drives the deep ocean currents, and the temperature determines the density of the water, so the thermohaline. And with the slowing currents and overall warming ocean temperatures, there'll be less movement of the important temperatures that affect all of our climates here in the Atlantic region. If we look back at this picture, specifically part B, it kind of shows how that circulation is affected by salinity. So it shows the circulation strength. Their example is the AMOC, and it goes for it's this positive feedback loop. So it goes to saltwater influx, and then surface water salinity, and surface sinking water, and that determines how strong the circulation is. And a little bit more on that. So the high salinity and low temperature is what really drives the deep ocean currents that produce the AMOC. And melting glacial ice is decreasing the salinity in the ocean. Scientists mostly focus on the Greenland ice sheet, as it is all freshwater, and it is rapidly melting and changing the salinity. The decrease in salinity is destabilizing the AMOC, And models struggle to reproduce this because the AMOC is a positive and negative feedback loop, so it'll stabilize in some regions while it destabilizes in others, so it's really hard to predict where and when that will happen. And weakened currents. So decreased warm water flow north would decrease temperatures in Europe. Some models predict that France and Scandinavia could be covered in snow for 4 to 8 months of the year, and significant loss of biodiversity from the changing ecosystems due to these climate changes. AMOC slowing will impact Europe's biodiversity more than any other climate change factor would. And then this top picture shows different models that the scientists came up with, but you can kind of see they're kind of all over the place. None of them are very stable. None of them reproduce each other, so it's kind of hard to represent what the thresholds are and what will really happen if the AMOC stops, and what is the point where it actually did stop. And this one down here in the bottom is just a movie that came out in the early 2000s that kind of shows what might happen if the AMOC stops. It is based off of that. It's pretty much the Ice Age starts in the movie.
So now I want to talk about the summary of scientific evidence as to why researchers believe that AMOC is probably going to weaken in the near future. So in the article titled Expert Judgments on the Response of the Atlantic Meridional Overturning Circulation, which is AMOC, to climate change, 12 experts agree on a possible weakening of the AMOC under scenarios of increasing greenhouse gas emissions. And just like most researchers outside of this article, many people might disagree on the way in which we know that the AMOC is weakening, or the extent of its weakening, or even possibly what will happen if it does weaken. But at least these 12 experts definitely agree that a weakening will happen. This article was also published in 2007, which means in today's world, the weakening of AMOC is believed to be even more possible due to increasing greenhouse gas emissions. So now let's look at some of the signs of destabilization. What's happening that makes us think that AMOC is weakening? So in general, they've noticed a 15% weakening since the mid 20th century. And this is known to be weakening because of a rise in instability of the ocean currents, mainly the sea surface temperature fingerprint. The sea surface temperature fingerprint refers to the identification areas in the North Atlantic Ocean that show that something is abnormal. So there's areas of the North Atlantic that have cold blobs, which means that these locations are colder temperatures than what's expected to be normal. This indicates that the ocean currents must be changing because the temperature is changing. And so the cause of all of this is what scientists believe is the melting of the Greenland ice sheet. So between the years of 1992 and 2018, the sheet has lost approximately 3,902 gigatons of ice. The melting of this ice sheet has led to a large influx of fresh water into the North Atlantic Ocean. When that amount of fresh water enters a salt water environment, it disrupts salinity levels and completely changes the way that the ocean currents and convection currents operate. Additionally, another big indicator that AMOC is going to weaken in the near future is the fact that there's record that it has weakened before. So Heinrich-Stadel 1 was a significant climate event in which glacial melting led to meltwater input into the North Atlantic. This large amount of fresh water led to a southward shift of the tropical rain belt, which means certain areas that expected lots of precipitation were then experiencing levels of drought. So lastly, based on all this scientific evidence, if AMOC were to collapse, scientists predict that by 2060, the European climate would significantly cool. In summer, the climate would cool by about 2 to 4 degrees Celsius, and in winter by about 2 to 8 degrees Celsius. And just like I previously mentioned with the tropical rain belt, scientists expect large changes in precipitation levels, and in general, they expect precipitation to decrease across the globe. Um, Additionally, global seasonal weather patterns would fluctuate. This is because of climate changes and weather patterns, such as precipitation, that would alter, and then seasons wouldn't be the way that we see them now. And finally, they expect a rise in sea level in the North Atlantic Ocean. AMOC collapse in combination with increasing melting ice and increasing global warming are all going to lead to a rise in sea level. Scientists expect a range of 10 to 20 centimeters by the year 2100. And finally, these are our sources that we use to complete this slideshow. And all of this, there's a lot of research out there that shows that AMOC will likely weaken, and it has weakened in the past, and that it will lead to detrimental changes in the way we see climate and weather today.